In this lecture, we're going to fill in the missing detail from the last lecture. How do we calculate the dimensionality of the initial feature vector into the dense layers of a CNN? For this, we need to know about a topic called convolutional arithmetic. Basically, these are the concepts that allow us to calculate what the output size of a convolution will be given some input size, some filter size, and various options such as padding and strides. As a reminder, the reason why we need this is because PyTorch requires you to specify both the input size and the output size of each layer, even though we implicitly already know this information. What's weird is that these calculations are well defined, so there isn't really a great reason to require us to do them ourselves. Libraries such as Keras make things super easy by automatically inferring the input size of each layer, so you only need to specify the output size. The reason I mention Keras a lot is because Keras is usually a student's first introduction to deep learning. And even if you don't know Keras, you could easily pick it up in a few minutes, provided you have some base level of programming skill. So another great thing about Keras is that it allows you to pass in a string to specify the type of padding that is used for convolution. As a reminder, we generally have three modes of convolution. In valid mode, the output size is n minus k plus 1. In same mode, the output size is just n, the input size. And in full mode, which no longer exists by the way, the output size is n plus k minus 1. And remember that these are just the basic form of convolution with no strides. So you might think, well, that's great. If I just use same mode for all my convolutions, then calculating the output size is super easy. But wait. Passing in the mode of convolution as a string exists only in Keras, not PyTorch. The reason I mention this is because it's a natural question to ask. Why not use same mode so that it's easy to compute the size of the image after each convolution? If we do that, then let's say we have an input image of size 32 that goes through 3 convolutions with a stride of 2. After the first convolution, the image shrinks down to 16. After the second convolution, it shrinks down to 8. And after the third convolution, it shrinks down to 4. Easy. Well, let's ask ourselves, how would we do the equivalent of same mode in PyTorch? Let's see. We have to specify this padding argument, which tells PyTorch how many spaces to pad the input image on each side. But wait, in order to specify this argument correctly, so that you achieve the equivalent of same mode, you need to do convolutional arithmetic to calculate the correct amount of padding. In other words, you still need to do convolutional arithmetic whether you have same mode or not. So there's no benefit to using same mode because either way, you still have to do convolutional arithmetic. In fact, this might be a little harder because you have to do convolutional arithmetic in reverse. The only good reason to use same mode would be if you really believe it benefits your model's predictions. Okay, so now you're convinced that there's no way out of doing convolutional arithmetic. In this course, it's not my goal to go in-depth about this topic. If you want to gain a better intuition about convolutional arithmetic, I've left a link to deeplearning.net in the file extrareading.txt, which leads you to a tutorial about convolutional arithmetic and how the calculations change when you have padding, strides, and so forth. It's pretty non-trivial. However, an easy way to get around this is to simply use the formula that PyTorch provides in their documentation. With this formula, you can plug in all your values and calculate the output dimensions. You don't need to understand convolutional arithmetic to use this formula, you just need to know how to multiply, add, and divide. Let's do a simple example to make sure you know how to use this formula. Since the formulas for both the height and width dimensions are the same, we only need to do one. Firstly, the concept of dilation is outside the scope of this course, and we will use the default value of 1. Next, let's assume we have padding equals 1, kernel size equals 3, and stride equals 2. Let's set h in to 32, which is common for deep learning image datasets. If we plug these values into our formula, we get 32 plus 2 times 1, minus 1 times 3 minus 1, minus 1, all divided by 2. then we plus 1, and then take the floor. So that gives us 31 over 2 plus 1, which is 15.5 plus 1, which is 16.5. Then we take the floor of 16.5, and we get 16. So h out equals 16. Now it's easy to make mistakes with these, and I wouldn't be surprised if I did, so if you want to double check my work, please do. Alternatively, you could just implement this in code. You may have noticed something a little curious on the previous slide, which is that in the PyTorch documentation, the input size and the output size are specified as n by color by height by width. This is contrary to what we've been working with so far, which is datasets of size n by height by width by color. Why is there this discrepancy? Well, it has to do with the conventions of the library. Remember that when you're a programmer building a library, you have full control over how it works. So you get to decide what the conventions are, how you want to structure the data, and so forth. It turns out that some developers decided to put the color channel first, while other developers decided to put the color channel last. In our case, libraries such as Theano and PyTorch decided to put the color channel first. Libraries like OpenCV, TensorFlow, Matplotlib, and Pillow use the convention that the color channel comes last. Although OpenCV does other weird things like using the BGR color ordering instead of RGB. So it seems that putting the color channel last has now become more common. But PyTorch was built with the color channel first. We can't just switch it around one day and expect everyone to update their code. Therefore, PyTorch still uses the convention that the color channel comes first. This detail is hidden from you if you use utilities, such as those from the Torch Vision library. Since we haven't worked with color images yet in this course, we haven't had the opportunity to uncover these hidden details, but now we do. As you recall, if you inspect the data attribute of a dataset loaded in from Torch Vision, it gives you the untransformed version of the data. These will be n by height by width by color. But when you yield batches of data from the data loader, this data is transformed in whatever way is needed before it goes into the neural network. And so, when you inspect these batches of data, yielded by the data loader, you will see that they appear as n by color by height by width. So in fact, PyTorch still uses the convention that the color channel comes first, but it comes with interfaces that work with the more commonly used convention that the color channel comes last.